Welcome everyone to this Audio Engineering Society UK section event. Before this evening's event starts, I just have a couple of quick points to make. First of all, these events are open to both members and non-members alike. If you are not yet a member of the Audio Engineering Society, please consider joining us. We are a professional society of about 8,000 members worldwide, and as a member you have access to a great network of people, resources, events, both conferences, seminars and evening events or daytime events like this. Secondly, if you have any questions during this evening's event, please use the Q&A button at the bottom of the screen, and at the end of the talk we'll go through the questions and our speaker will answer them. So with that ado, let me close some stupid windows and introduce tonight's speaker. So Steve Oxnard, he is the 2025 Audio Engineering Society UK section chair, taking over for me. I'm now the past chair. Get to pass on the chattels of office. He began his career as a lecturer in sound and electronic engineering at Anglia Ruskin University while he was finishing his PhD at York. Then in 2018, he joined Meridian Audio Limited as a senior research boffin, conducting research in sound reproduction and loudspeaker management. So tonight's talk. Loud sounds can be felt as well as heard. Feeling a kick drum beat through your chest or a room-shakingly bassy sound. In this talk, Steve will dive into the study of audio haptics transducers, their measurement, evaluation, and use case optimization. He'll also discuss past and emerging technologies that employ haptics as an element of audio reproduction. And he'll cover some simple yet effective strategies to ensure that haptics systems give us some genuinely good vibrations. So that's enough for me. Time to hand the Zoom over to Steve.
Neil, thank you very, very much indeed for your kind words of introduction and for providing the overview for tonight's session. I am going to do my utmost best to get the difficult bit over with here, and that involves sharing screens and getting the presentation up. So we'll get this bit done, hopefully without any further ado. Now, I hope that this is now showing okay for...
Yep, that's coming through loud and clear.
Brilliant. Okay, perfect. In that case, off to a fine start. Okay, so I firstly just wanted to provide a bit of context for tonight's talk, in that I'm not used to doing a talk in this kind of setup. I've never done an online presentation before, so I'm very used to walking around and gesticulating quite a lot. So if I start raising my hands or playing with my face or whatever, it's just so I'm used to moving. Second thing is that I may or may not sort of call a break maybe halfway through this session, depending on how things go. And if we agree to do that, this will be just a couple of minutes, and then we'll get back to it. So oh, there we go. I'm just going to make sure this works. Yes, that's lighting up my face. Fantastic. Okay, so tonight's talk, haptics and audio reproduction. I have to say the introduction that Neil gave made it sound very exciting. Whether or not this lives up to that, we'll soon find out. So thank you very much indeed for everyone who's here live. Really appreciate your taking the time to be here with us. So the session is about some research that I and some colleagues have been doing on haptics. We're going to preface that with a look at some haptics technologies through the ages, and yeah, we'll start by looking at some very, very basic elements of the sense of touch. So haptics and how we perceive vibrations. Now, I've done a very, very cherry-picked history, I said selected history, of haptics and media and entertainment, starting from quite a while ago, and reaching into the sort of modern era. We'll then move on to defining audio haptics, very simple definition, and sort of setting the scene for the justification of the research that myself and colleagues have been undertaking recently to provide context for discussing audio haptic reproduction, and also the means by which we can assess or evaluate signals that are generated to drive haptics units, and also the response that the transducers can give us and the tuning of systems. We'll finish off with a case study, a recent case study, of a demonstrable audio haptic system, and close with future research and directions. Okay, so haptics, as a term, is derived from ancient Greece, and it came from the word hapticus, pardon the pronunciation, and that means tactile, or just pertaining to the sense of touch. And what we currently know is that humans are able to perceive vibrations. If you think about vibrations being sort of sinusoidal in nature and in contact with the body, we can perceive vibrations in quite a large frequency range, so 0.3 hertz to 1 kilohertz. And this vibrational transfer of energy is either through the air, so very high sound pressure level events can really buffet us in terms of air pressure or local air pressure, but then also sort of on skin or on body contact vibrations. This is a kind of perception that we're talking about with that frequency range. So there's clearly a big overlap between what we can feel through tactile sensation and what we can pick up orally in terms of what we hear. So this overlap then facilitates a congruent experience of sound, both through the oral response, but also the perceived tactile response when induced. So when we say when it's induced, it's either through as I say, very high sound pressure level events, the kind of thing you'd expect to pick up at a live show, or when they're forced through haptics transducers that are actually in contact with the body. So these tactile sensations are sensed through so-called mechanoreceptors. So these are nerve endings in your body that are everywhere, and there's various types of these mechanoreceptors, and you'll get the sense that I'm bottoming out my knowledge on the biology part of that, and that's exactly the case. So different mechanoreceptors are responsible for picking up and sensing different types of tactile interactions. So here I've given examples of pressure, flutter, and vibration. And by pressure, I mean if you were to displace the skin or the surface of your body in a local region, that displacement would be sensed, and there'll be some mechanoreceptors that are responsible for that. Flutter is like a sort of on and off contact, I believe, and then vibration is what we're interested in here, and that's actually where locally or globally you would have a sort of a close contact vibrational sort of impact, and the sort of contact based where a vibrating or shaking surface is actually in contact with the body is what we're mostly going to be talking about and using when we're talking about, when we're applying audio haptics. So the mechanoreceptor specifically responsible for this perception of vibration is the so-called Pacinian corpuscles. Again, with apologies for pronunciation there, if incorrect. And the active frequency range for this particular nerve ending is reported to be around 40 to 500 hertz. So we're looking at low frequencies and low to low mid frequencies. That plays a part when we come to actually look at the characteristics of haptics transducers later. We'll see that the responses usually top out around 200 hertz, and that's absolutely fine for use purposes. Okay. So just as a way of describing the different kind of mechanoreceptors that we actually have, the left diagram shows the Messiaen's corpuscle, the Ruffini corpuscle. These are responsible for other tactile sensations. The Pacinian corpuscle sort of located ever so slightly deeper in the skin. So it's just at the lower level of the dermis. So this is sort of just under the maybe call it the first layer of skin. Sort of where I think where hair follicle, where the hair cell starts. It's around that kind of region. And the diagram on the right is reported to be an actual picture of a Pacinian corpuscles. Why the color is the way that it is unknown. However, I just hope that gives some sort of idea of what's doing the job of facilitating the sensation or the perception of tactile interactions, and more or less what it looks like. Okay. So moving on to haptics through the ages, if you like. Going back to the very start, when I was reading up on where haptics kind of came from in terms of interactions, the first example that's commonly referred to as the first example, the first application of haptics technology, was the notion of an augmentation of experience as a safety feature, which I found quite cool. So the idea was that if you were in a plane and you were flying a plane, you'd have your yoke, or the equivalent of a joystick, and when your plane was at risk of going into a stall, and potentially having a bit of an issue, the stick would wobble and it would let the pilot know that they needed to do something, and do something fast. Apparently this came around in sort of World War II era. However, the first maybe commercially applied example of this was actually in the 1940s, apparently the late 1940s. So that sort of stands as a first application of actually using vibrations to augment an experience and get information to a person via means other than auditory, visual, etc. Then the first media example that I could find was this Sega motocross game. It was an arcade game, and the narrative, unfortunately, here is probably too small to read on the screen there. But if you're interested, you should go and check it out, because it has quite a good write-up of the sort of first attempt of hyper realism, I reckon, through this arcade machine. And basically the idea was you had a set of handlebars that you could actually control this thing with, and if you crashed or you hit another biker on the track, the handlebars would vibrate. And apparently this is the first use case of haptic feedback and tactile sensations in a game, in consumer media, really. Then just having a think about arcades and that kind of thing. You know, we're thinking about pinball. It's actually quite a tactile experience, I think, playing a pinball game, because you had all sorts of solenoids kicking off and all the rest of it. And I actually found that there was one that deliberately had haptic feedback built into it, and this was, you know, the next decade after that example of the Sega Motocross, but it had haptic feedback in it. And then this idea obviously took hold in a way, and then started entering into the home along with games. So gaming consoles came from the arcade into the home, and a bit of haptics came with it. And this Aura interactor is one of the earlier examples of something that you can actually wear and plug into your I think these things were compatible with Sega consoles as well. But the cool thing about this example is it was actually driven by audio. So it had quite a simple interconnection, and it fed the audio from the game, and took from the low frequency effect, although I don't think low frequency effect was a dedicated channel at the time. I think it was the signal manipulated, and it would pass the audio into this wearable device. I felt a bit bad for the Aura interactor, actually, because the best picture that I could get describing it, you can see the link, was the worst Christmas present ever, which I want to check this out for myself, so I think I'm going to pick one up on eBay, and they are available. So continuing with gaming, these controllers are more akin to what I was familiar with growing up, and this became a staple. So prior to this, controllers were, you know, they were just very simple, very lightweight, not very well ergonomically designed. And then the rumble packs came along, or the DualShock is the one that I was mostly familiar with. And then there was literally no going back from that point. These came into play. Nintendo apparently got there first with the N64 and their detachable rumble pack, and then Sony followed on. And I don't think there is a gaming console out there that would dare not have this kind of technology loaded into it these days. Then more modern gaming systems, even more modern, going from the controller, where you're interacting and you're picking up an augmented sense of what's going on in the game through your hands, to increase the immersion and, you know, get you properly engaged with the game. This is now going into, you know, like with the Aura interactor, except it's your seat, all sorts of body contact haptics units that can basically accentuate things and events that are going on in your gaming world. And these, I would say, having a look online at the kind of things that you're able to get these days, like gaming rigs and gaming chairs, some of them are extremely advanced, and have a lot of technologies put into them. Some of them look quite scary in terms of the amount of things that they can do. However, the use of haptics is clearly in gaming becoming more and more prevalent, and it's being, you know, it's gone all the way from a small device that could possibly shake your chest a little bit, that's driven by an audio stream, all the way to, you know, well, through rumble packs for your hands, all the way to full body things that you can wear, VR suits. There's things that, you know, you can strap to your wrist, to your torso, to your back, everywhere, that can pick up cues from virtual reality that's running over headsets to give you all kinds of tactile input from your virtual world. So just as an aside, obviously the gaming side of things wasn't the only place that haptics is becoming prevalent. It's almost we say another way of saying, you know, it's taken for granted that it's there in mobile phones. Mobile phones have been vibrating for a long time. Smartwatches, handheld gaming devices. So even the old Game Boys, I believe, had rumble packs that you could actually slot into these into them. Touchscreen devices for that little bit of feedback that you get when you type in a digit, just to make sure that you know that it knows that you've done something. And as I mentioned, virtual reality suits, even getting used for things like medical training, and the idea of telepresence, so you can interact with a totally different environment over some communications link that's elsewhere. Can engage through gloves that are able to give you some sort of tactile input from somewhere displaced. Now, this is where we're going to draw a distinction. So with games consoles, it's not a case of strictly just having haptics that was audio related or completely consistent with the audio in a game. There could be various other things going on that were giving you the haptic, or the haptics were being used to accentuate. So audio haptics techs, we're talking about stuff that is specifically augmenting the listening experience. So they are putting forward and allowing a listener. I know listeners at this point is a bit of a daft term to use, because you're not only listening, you are feeling it as well. So there are various. I mean, this obviously is not the extent of all the products that are available currently to do this kind of thing. But we've had companies like FlexSound came about a few years ago, and they developed a sort of speakerless chair. So their idea was to use haptics transducers or shakers within sort of cinema seats to give not only sound but also a tactile rendering. You couldn't really do one without the other with the way this technology works. Subpack, these are sort of wearable things, and they do quite a lot of processing on the input audio stream to generate a tactile experience alongside the audio. And it's exactly the same principle with this feel belt from Senses. So audio-driven haptics that are either sittable or wearable, these are becoming quite common and have been in development, for a decade now. But more options are coming out all the time. So further uses of audio haptics is, well, one that's becoming more prevalent, and one that's of interest to the company that I work for, Meridian, is automotive. So actually putting haptics units into seats, car seats, to augment the listening experience, to provide a more exciting means of reproduction. And another more sort of like niche, I say niche, it's kind of cool, these butt kicker devices. I think they've been around for a while. They're not only they don't only do this one specific example that I'm going to talk about. They also do things for gaming. But this was quite a cool notion, is that you can just see it. it's actually attached to the drum stool. It's apologies if the picture's a little bit small, but the lead out that's going into the drum stool with two terminals, it's actually a haptics shaker. And the idea behind this is that you can use it in live sound for a drummer to have as part of their monitoring system, so they can feel more engaged. So instead of having a big, I'm assuming instead of having a big drum fill sort of stack with subs and all the rest of it, you're blasting it into the drummer, they can have this device under seat that can be congruently used with in-ear monitors or an alternative, and give them a real sort of sense of engagement with what's going on stage and what the crowd are getting more to the point. So, okay, quick check of time. Good. All right, so hopefully that sets the scene a little bit in terms of what haptics is, where it's come from, what it's been used for in the past, and the applications are many. And it should, maybe it's not so obvious, but there's a lot of research out there from the more biological, physiological, psychological realm about the sensation of touch. So there's a lot of work, a lot of research out there on how we interact with the world around us through touch. And the motivation for the research that we've done, that I've been engaged with recently, comes from the notion that there's not a lot, well, let's say notion, a perceived fact that there's not a lot of work out there about audio haptics specifically. So actually using haptics devices to augment a listening experience. That seems to be quite sparse in the literature. The other thing is that if we think about ways of figuring out what is good haptics, what is a good haptics transducer, what makes a haptic system pop, how do we tune these things? There's very little information out there, and more to the point maybe is when you're going out and you're trying to select one of these devices to use, a commercially available off-the-shelf unit, usually what you'll get is a max power handling, the kind of power that you can put through it before the thing melts, and a really nominal frequency range, which is kind of meaningless almost, because if a loudspeaker is able to recreate frequencies up to 20k, then we kind of know that we're going to be able to hear, well, I probably wouldn't be able to hear that, but we'll be able to hear quite high up. If a haptics transducer is able to recreate anything up to 200 hertz, is it going to be flat? Is it going to be stable at that frequency? How much distortion is it going to produce? Is it, I mean, if it's capable of moving at 200 hertz, doesn't mean it's going to have any kind of output in terms of what you can feel from it. The other thing is that if we have audio content that we're listening to, what kind of signal makes sense to put into a haptics transducer in order to feel the sound at the same time? So how do we actually generate or derive these signals? Again, this is something that's quite underdocumented. Subjective evaluations, we know a lot about how we perceive sound through our ears. We know very little, I think, about how we feel sound through our bodies, through the skin. And then just as a sort of overarching kind of idea, what I'm getting at here is if we compare haptics transducers in an audio sense to loudspeakers, we know basically nothing about haptics transducers. We certainly haven't come up with any, to my knowledge, standardized metrics or testing methodologies or any of that kind of stuff. That, you know, these things have been in place for loudspeakers for ages, but then loudspeakers have been around for maybe longer in the audio realm. So that's kind of the notion behind starting out with this kind of research. What I'll do now is just very briefly go over some initial research that was conducted by the team at Meridian, and then I'll go on to a couple of case studies really on haptics transducers. The idea here is just to put forward some notions, and then we'll dig into more detail through the case studies as we go. So the first piece of output that we had was this paper at the 154th AAS convention back in 2023. This was headed up by my colleague Ethan Stanhope, who looked into what kind of signals we wanted to use to drive haptics transducers when we're trying to recreate audio that's congruent and consistent with the audio that we hear. So the motivation here was, if we're looking at program material or common music, there's not a dedicated, this is the haptics track. It can have an LFE, but you know, if you're just listening to stereo audio, what should be driving the haptics? And what was looked at is various methods of doing bandwidth extension, because quite a lot of content doesn't have a lot of energy below, say, 100 hertz. So the idea was to maybe make it up in a way. So we looked at different things like pitch shifting, some distortion, and synthesis to actually, you know, generate haptics, a tactile signal. But what we found, or what was found, is that there was very, you know, little evidence to support the claim that bandwidth extension really brought anything to the table over having audio that was bandpassed to whatever the haptics transducer range was. Say, for instance, if you took everything up to the first 200 hertz of a stereo track, and you had a left and a right, and you sum them together, put them through a transducer, that could be as effective as reaching for a synthesis method that could give you more energy down the low end. This idea of preference came into play through subjective testing. It became very apparent very quickly that everyone preferred different things for different types of music. So the notion of user control and customization based on personal preference was mooted as a result of this research. So there was two takeaways that were quite useful amongst others. First one, we can use the audio bandpassed, and we generally don't really need to make up anything extra in order to get a good haptic effect. The second thing was that opinions varied quite vastly on what was good and what wasn't. So having someone tune their own, having control over what they wanted to feel, or the type of haptics that they wanted to feel, depending on genre and the type of music they were listening to, that was highlighted as quite important. The second part of the research was more geared towards actually looking at the transducers themselves and getting an idea of how we could characterize them, measure them, find out a little bit more about them, because again, we're coming at this with maybe 2 bits of information for one transducer that said, yes, you can put 50 watts through it, and yes, it will give you down to 20 hertz, and that's all you know. So what we wanted to do was have a way of measuring them and comparing them. That was it. It was very, very straightforward. At the same time, we looked at how we could manipulate the input audio to make it maybe more punchy or more rumbly. And this was drawn from alongside the findings that we were generating through subjective testing. If you wanted to listen to EDM, then you wanted something that was very tight and punchy. If you wanted to listen to classical music, you don't suddenly want to have a timpani drums, you know, going into your spine. Instead, you want something quite smooth and quite rumbly. So you'd have this sort of means of controlling whether or not you want more transients or more steady state enhancements. And this was done through reasonably rudimentary microdynamics control. When it came to characterizing the drive units in a comparative sense, we're using accelerometer measurements and taking impulse responses. So we put a sine sweep through these devices and collect an impulse response from each. And based on that, we drew metrics from the world of acoustics, so early decay time and C50 or clarity, an energy-based value, to have a look at whether or not we could draw any sensible information from impulse responses. Ultimately, we could, but the use of these parameters specifically wasn't overly reliable. And in terms of comparing with and without pre-filtering, as I've mentioned here, this will become important in a moment when we talk about anti-resonance filtering. So, alongside or sort of round about the time we were developing and conducting the research, we published a patent, or put forward a patent for a haptics system, which used the transient to steady state manipulations and provided user control over these, and had the idea that if you had a system that had more than, or maybe one or more haptics transducers in it, depending on where that transducer is positioned relative to the user, what kind of signal should it be given? So what we effectively, a big part of the patent, I think, or a useful part of the patent, as far as I'm concerned, is this idea that you could tune individual transducers depending on where they are relative to the person. And if we think, be a good example. So if the haptics were under your feet, maybe expect things to be more rumbly and less transient. If the haptics were positioned in, you know, at your back or your chest, you would expect them to maybe be a little bit more punchy at times. So that was the idea. So we had microdynamic control to blend between punchy and rumbly. And then the idea of distributing these tuned or location-specific signals to different transducers. And it was also dependent on the type of transducer as well. So it might be, yeah, it'd be worth at this point just noting that haptics transducers come in all shapes and sizes, things sort of this size, very weighty to tiny. And depending on what kind of transducers you may or may not be forced to use, given a use case scenario, it could be that you would want to mitigate rumble or mitigate punch, and you can optimize the signals based on the kind of transducers that you have. Okay. Now, taking the idea of characterization of transducers a little bit further, we came up with two metrics that were solidly based on the two that we had used previously, so early decay time and clarity, drawn from the impulse responses. And instead we used fall time and this transient to late energy ratio. So as I say, the basis for these two metrics very much akin to the two that we drew from the world of acoustics measurement. And these two metrics were used to have a look at the impact of resonance reduction, because what we were wanting to do is get as much control over these units as possible, thereby tightening up the transient response. And if you manage to minimize the amount of energy that was in the decaying portion of the impulse response, the idea was then you would have more of a more control over what you actually put through it and what was experienced at the other end. Now, we also looked at crest factor measures to see whether or not these would be useful for measuring the impact of the dynamic modifications that we were doing. So we're looking at transient extraction and steady state extraction, or suppression of either. And results are mixed. So crest factor, it's there in the paper, it's there in, I believe, the last paper, the case study, that I'll come to towards the end of this talk. But I'm not going to spend a lot of time looking at that element specifically, because it takes quite a lot of discussion to get the point across of what we actually found using crest factor. So our first study for tonight, again, I'm just going to do a quick time check. Okay. Based on the previous paper that I just talked about, we wanted to look at the measurement of transducers, not so much in isolation, but they are in a fixed condition, and this means that they're loaded, they're actually attached to a surface. So again, 3 transducers. We want to see whether or not the metrics that we were using and the measurements that we were drawing these metrics from were useful in terms of giving us information that we wanted. We also looked at excursion modeling. So we're seeing whether or not we could predict how far these things were actually moving, so that we could protect drive units against over excursion and damage, essentially. So, as I say, 3 haptics transducers, and they were fixed to a mass that was at least 10 times the mass of the unit itself. So that is nominally accepted as a fixed condition. When it came to actually measuring these things, I should say they are moving mass transducers. So this is as opposed to a loudspeaker where you have a voice coil that's shifting with a cone. The voice coil is actually around the outside of these units, and the magnet is the thing that moves. So what we did was attached an accelerometer directly to the magnet to actually get that as our point of reference of what was going on in a transducer, or what we could get from a transducer. Electrical measurements, just straight across the terminals, very similar. Well, it is exactly the same as taking an impedance measurement of a drive unit, and we use that to derive our Theo Small models that were then in turn used to create the excursion models. So to get the impulse responses, we're just taking sine sweeps across the active range. I mean, 2 kilohertz is probably a bit high, really, even still. And we did measurements at 1 watt, and the reason will come clear, and then proportions of the unit handling. So one unit was capable of doing 50 watts, another unit was very small, it was capable of doing 1 watt, I believe. So proportionally, it was decided that we would look at the relative kind of levels of input power per device. And then, yes, we used a simple electronic drum track, so simple drum samples to have a look at the correctness of the excursion model that was derived. So first step, impulse responses with resonance reduction. So driver 1, 2, and 3, 1 was very small, 2 was medium, 3 was very big. And what we can see, or really the main takeaway from this, is that the first small drive unit already had quite a tight transient profile. And through resonance reduction, as you can see, it's not as peaky in the lower frequencies as the other driver unit, particularly driver 3. That's very, very resonant at low frequencies. So there's actually not that much change in terms of the transient shaping that's been brought about through resonance reduction. We do see improvements in drivers 2 and very much an improvement in driver 3. We can see that the resonance reduction, if we just imagine that the peaks in the graph on the left-hand side have been flattened out somewhat, the time domain representation is on the right, and we can see that the resonance is greatly reduced, and there's a lot less ring in the system. Now the metrics, these were the things that we wanted to use or apply and see whether they would give us an indication or a means of evaluating and comparing drive units. First thing was force potential. So this was equivalent to a sensitivity measurement of a loudspeaker, where you put 1 watt in, you measure from 1 meter, and you see what kind of dB SPL a drive unit is capable of producing. So we do 1 watt and see how much force it can generate. And this is simply F equals ma. So the moving mass multiplied by the acceleration that's rendered or recorded, and we have our force potential. The fall time is derived from the energy decay curve, so sort of Schroeder curve, and we're looking at the time it takes for the energy decay curve to reduce from 90% to 10% of its initial value. So this is like the rate at which a unit is capable of slewing between states, an active state to an inactive state, or vice versa. Well, vice versa would be rise time, but we won't get into that. Transient to late energy ratio. This is very much like the clarity index, except we're not looking over the first 50 milliseconds or 80 milliseconds. We're actually looking at just the first event in an impulse. The definition of that has changed over the past couple of years. But essentially what we're looking at is just the very first peak and trough, and the amount of energy that's focused in that area versus the amount of energy that's in the remainder of the impulse tail. And yes, in the paper, there's the idea of rise time and transient to total energy ratio. We didn't use them, but for the purposes of putting the idea forward, they were added for completeness. Excursion modeling. I'm going to skip over this rather quickly, but essentially we have a teal small lump parameter model where we can translate the voltage that we're putting across the unit into the displacement of the moving mass or the magnet. Then we can find the characteristic displacement versus frequency, and then in turn model that using a second order low pass filter that fits the same profile of displacement. What we can then do is put audio into this entire system and see what the excursion should be and predict it, and then see whether it's realistic after we've measured the displacement directly from a drive unit. So first point of interest was the impulse response measurement in the frequency domain for different levels of proportional input power. On the left, rather, we have the small drive unit. And what we can see, which is quite nice to see, is that for a quadrupling of input power, we had a doubling of displacement, which was cool. And this is, particularly apparent around the peak, around the resonance. In the case of driver 3, which is the big heavy unit that took a lot of power, we can actually see that it's not quite the case that we're getting a doubling of displacement for a quadrupling of input power. The thing's actually kind of topping out towards some form of limit. So we've got some nonlinear behavior going on here. So that's insightful, kind of useful. The first metric, force potential. This is the amount of force the unit is capable of producing for 1 watt of input power. And this is quite revealing in a way because it gives you an idea of bang for buck. And if you have a low power system that you need to drive some haptics transducers off, what transducers are you going to reach for? Are you going to reach for ones that have a high power handling? Are they going to be big, small, medium? Don't know. What this shows you is how forceful a unit can be over frequency for a given nominal 1 watt input. So as an example, if we wanted a unit that was only to produce 100 hertz and above, we would pick driver 2 because it can move more for 1 watt. So that gives us just a little bit more information about what a drive unit is capable of. And this, as we stated, is meant to be akin to a sensitivity measurement. Now, what I'm going to focus on here are the results of applying resonance reduction. So if we just quickly dial back to the impulse responses again, we can see there's maybe not a massive change in terms of decay time for driver 1. There is a little more for driver 2, massively for driver 3. This is reflected in our measurements of fall time, so the slewing between states, the amount of time that takes, and the transient to late energy ratios. So we can see not a massive impact in terms of reducing the fall time for driver 1 across all input power levels. But what we can see that's quite interesting is an increasing consistency of the times across different proportions of input power. So that was quite cool to see. And this is also the case for the transient to late energy ratio. After resonance reduction, we see mostly a decrease because of this smearing, time smearing that's brought about by the resonance reduction filter, but a higher level of consistency, which is interesting. For drivers 2 and 3, the results are clear. When we apply resonance reduction, we get a tightening of the impulse response, thereby a quicker fall time and a much higher transient to late energy ratio. So good results. Basically, this means that we have a reliable metric that's able to tell us that whatever strategies we apply to tune a system towards having maybe a faster or slower transient profile, we can reflect this characteristic using these measurements, which is useful. The results of excursion modeling worked really well for driver 1 and driver 2. The actual percentage errors and whatnot are noted in the paper. As we can see, it's gone a bit wrong for driver 3. There's quite a large margin of error between the measured and predicted excursion. But on the whole, 2 out of 3 isn't bad. And it should be noted that the models, these are only first pass models, so it was literally first go at deriving a TS model. These things, the models can be tweaked depending on well, you could tweak them to give you a better prediction just by tuning the model appropriately. So for a first pass, this was good, and it meant that if and when we need and want to, we can apply excursion models to save the transducer from damaging itself if it's being overpowered. Okay. So lastly, a case study. And I'm going to rattle through this because I'm conscious of time now. So bear with me. This was fun. From going from the comparative sort of measurements and looking across various transducers in a kind of isolated scenario to measurement of an actual person interacting with these devices. This was good fun. So really we got a device and stuck it to a chair, and then got people to sit on the chair and measured it. We took impulse responses with different power levels. We looked at resonance reduction again, and then we also looked at excerpts of music. So there was a punk rock excerpt and there was a classical excerpt. So with the resonance reduction, really, we were looking again, we had where do you apply resonance reduction? If you have someone sat on your transducer, have you changed the entire system? Does the resonance still make sense? In this case, it did. The resonances were for all 4 people. They're all shown here in different flavors of black and gray. 4 participants, and the resonance frequency was the same, and the Q factor mostly the same. The amount of reduction, we didn't want to overfit to one case, so took a sort of nominal idea to build up a biquad filter to just flatten these responses out. And these are the results. So interestingly, there's 3 occupants out of 4 that look very similar. So the four levels are different input power levels, but they're all normalized. And you can see that we've got an outlier in case 2 with a very quite sharp transient profile. The gray is pre-resonance reduction filtering, and black is post. So we can see that in all cases, the resonance reduction filtering is tightening up the transient response as we want. Again, post resonance reduction, the energy decay curves are shown in blue for all cases, and then an average. Resonance reduction filtering shown in black. So this is just showing us the step towards deriving the fall time for this system, the energy decay curve. We can see the amount of change brought about in terms of the transient profile shaping through a simple resonance reduction filtering strategy. Again, it's reflected in the results. So we have for all 4 all 4 participants, subjects, fall time is greatly reduced. The transient to late energy ratio greatly increased for all participants. And this was, again, it's useful to know the metrics that we're using and the way that we're measuring these things out. We can safely say at this point that they characterize a system in a way that is useful to us. And because the results and the trends were the same for each participant. So not only are we able to measure out individual devices and compare them, we can now measure out a system with someone in it and get useful data from it that we can then use to make decisions, essentially, or design decisions. Okay. A last little piece of analysis. This was new for this particular study. It was looking at cross correlation between input and output. So excerpt 1 is a punk rock excerpt. Excerpt 2 is classical music. And what I wanted to know was whether or not the resonance reduction was creating a more linear system, and that the reproduction was more transparent or more true to the input audio. And it turns out that it is when used in combination with a microdynamics process. So modified here means that in the case of excerpt 1, it was transient enhanced. In the case of excerpt 2, it was steady state enhanced, so the transients were diminished. But post resonance reduction, we can see that the correlation between input and the actual recorded displacement of the driver here, sorry, the membrane underneath of a listener, apologies, it's actually in context. The cross correlation increases when we apply resonance reduction, which means that our system is becoming more true to the original audio that's being put through it. And we think that's probably quite important for a good, immersive, congruent, oral plus tactile listening experience. Okay, so in summary, again, we applied the measurement and the subset of the metrics to a sort of more real world scenario, and found that the metrics are capable of reflecting the changes in the system that can then, inform tuning strategies. The cross correlation, as I've just mentioned, shows that the resonance reduction is really good for improving the sort of transparency of the system. Okay. All right. Key takeaways, then we'll wrap up. Transient performance, the dynamic control of haptics, transducers. Two things are key. Resonance reduction, definitely. The microdynamic control to either enhance your transients, give you something nice and punchy, or steady state to give you something rumbly. That should be, I think, personal opinion, should be user controlled, because it's very genre changeable. The evaluation of the system is possible using these two metrics that we derived from the world of acoustics, so fall time and transient to late energy ratio. The force potential, again, just another useful little bit of information when you're looking at system design. Drive unit excursion, very important if you don't want to blow things up. So all of the above plays a big role in creating a decent, enjoyable haptics experience. Looking to the future, obviously we just want to do more. I say more of the same. We'll learn as we go, and get these things as exciting as possible, and working as well with the oral part of audio as possible. This would then give us even more faith in our metrics of being able to represent and evaluate systems under use conditions, like actual systems with people in them. And then broader subjective testing and evaluation to see what user preferences are like, and how much control we should or should not be giving end users effectively. All right, so last little bit. Looking forward to the following year as chair, with a brilliant past chair, Neil, an equally brilliant committee around me. So yeah, really looking forward to it. The program events is underway. It's under development. Keep an eye out for the newsletter. Suggestions for talks, events, any kind of outreach engagement, always more than welcome. And lastly, thank you so much for being here with us tonight. Really appreciate it, and look forward to more of the same. Thank you.
And thank you, Steve. That was a brilliant talk. I feel the chair moving underneath me as you were speaking. And we're getting lots of thank yous from the audience as well on the chat. That's brilliant. Thank you very much, Jamie, Eric, and friends. And we got some questions as well. So how are you feeling, Steve? Are you ready to go straight to Q&A, or do you want to...
I'm okay for Q&A. Yeah, thank you. Yeah.
Okay, brilliant.
Sure.
Yeah, thank you, Greg, as well. Really good talk. So let's go straight in with... I did see someone had their hands up.
Yeah, I noticed that as well. Apologies, I did totally
Yeah.
skip over it.
So as I said at the start, if you could, any questions you have, please put them in the Q&A so that we can make sure that those questions do get answered and not interrupt the flow, as it were. Okay, so first question comes from John, one of our Cambridge members. What are the timing requirements analogous to lip sync with video?
So very good question. Requirement wise, off the top of my head, I do apologize, I cannot say exactly. However, there are a lot of there's a few studies out there that give a notion of what the boundaries are, but it's extremely important to get these things time aligned. So what I can say is that if you get it as close as possible for time of flight to the actual onset of the impulse response you record, if you can record these things simultaneously, you will find there's actually quite a lot of discrepancy in terms of natural time disalignment. So if I stopped sharing.
Yeah. Because I know there's an ITU paper recommendation for the sort of valid range for AV sync for normal streaming, but I guess for this sort of lower frequencies, then there are other factors involved as well.
It's extremely jarring if you get it wrong. And you can
feel the boom before you see the boom, kind of thing.
Yeah, exactly. And if it's better late than early, I think. Again, that could be a personal preference, but if it arrives before the sound, that's more unnerving than being late. I really do want to find out whether I can quickly dig this out. It's one of those things that I really should know off the top of my head, and I just I haven't got it in front of me. So I tell you what, actually, if we were to go to another question, and in the meantime, I'm bringing up the document that may or may not be able to tell me. So we'll come back to it if that's okay.
Okay. Yeah, I'm sure that'll be fine. Okay, so next question is from Eric Zaro. Could you share more on the transient reduction method?
Yes. Okay. So it's very straightforward. Take an impulse response measurement, have a look at where the resonance is, find the Q, find the gain, and biquad. That's it. You can find some systems will have multiple peaks. You can take out maybe two or three. But really the strategy is that simple. You can match decay profiles to the gain in the Q, or sorry, there would be negative gain because you are taking energy out of the system. But that is the up and down of the resonance reduction filtering step. It's a series of biquads that are based on the resonances that you have. So it's very straightforward. Didn't really find any need to correct for things like phase alignment, not at this point anyway. So as it stood, it was very keep it simple, but extremely effective. Yes. Extremely effective.
Brilliant.
And extremely important. You don't find these kind of resonances in well, you'd hope not to anyway in loudspeakers. So obviously you don't need to start already pulling out energy in a system. But when it comes to the haptics transducers, you really do find that these things are prevalent through all cases. So we're just putting it out there that you don't want to just low pass an audio signal and stick it through a transducer. If you do just that little bit more, the effects are astounding. It just becomes so much more true to what you would expect, rather than bulbous and light, or it swells. You get overlap between things that are going on in the audio. If you have rapidly occurring low frequency events, they're all just getting muddled up. Bit of resonance reduction and it just tidies everything up. It's very effective.
Okay, good. Next question's from Jamie. Driver 3 in your plots earlier showed signs of compression, so perhaps the linear field small model couldn't fit?
Yep, that's certainly a notion. The thing was, though, is that absolutely did see the drive unit reaching its, I should have said this, so apologies for leading you up the garden path with this one a wee bit. The power, when we put full power through the drive unit, yes, it did compress. It was probably reaching its limits of excursion. So they overstated how much this thing was meant to be, like, could put up with. Realistically, it couldn't. But with the excursion model, what that plot was showing was actually it running at a quarter of its power. So yes, there probably are non-linearities there, but I don't think it's to do with the compression brought about by the magnet actually really stretching the suspension. So we need to revisit that one and figure out what's going on. But it could well be that, yes, the non-linearities, wherever they may be arising, could well be to blame.
Okay, thank you. Next question from June Kim. Do you think there is any way to convert sounds to signal outside of percussive impulse?
Yes. Sorry, could I just have the question again?
Do you think, is there any way to convert sounds to signal outside of percussive impulse?
Absolutely, yeah. You can turn anything into a haptic signal. You can choose to enhance it if you'd like to. You could make it more percussive yourself through any kind of signal manipulation if you wanted to. You could do some very strange things. So yes, certainly. Even if you had something that was outside the range of the transducer, like a mid to high frequency event that the transducer is just not interested in reproducing, you could reflect that down into the passband of the transducer through a bandwidth extension method and get something from it if you really wanted to do it that way, to push it that way. Yeah.
Okay, just conscious of time. They've got 4 questions in the box, so we'll go through these 4 questions.
I'll rattle through my answers as well. And just coming back to the timing, the information is out there, but I just cannot find it. All right. So
yeah,
I do apologize.
Yes, it's yeah, nice little reply from out there. So next question is from Wayne, asking, have there been any considerations of transducer design changes to reduce the resonance?
Not that I'm aware of. A good question, and no, resonances just seem to be a thing. It's generally accepted that they're there. Given that the strategy that was shown to reduce the resonance is very, very simple, quite cheap in terms of DSP. If you had a passive system, it might not be as easy if you were building, an analog filter to do this stuff. But as far as I'm aware, I don't think, I wouldn't say no thought's gone into it whatsoever. It clearly has. There's a lot in terms of the design here, but actually reducing the resonances, I'm not sure whether or not it'd even be possible, because sometimes you're moving just such a massive mass. So yeah.
Next question is from Keith Howard. Not a single mention of fidelity here, nor any attempt to characterize what human listeners experience in respect of in respect of body vibration in different music listening circumstances, concert hall or home or whatever. How can appropriate levels, as opposed to liked levels, be assessed without this?
Fair point, well made. It's early days. We could. There's a notion that what could be studied is the natural response that you would get in an environment, and then the recreation of that. So if you're wanting a system that was capable of providing fidelity, we would need to know what that fidelity is meant to represent. So the real world system would have to be measured and then recreated. So absolutely right. This isn't something fidelity hasn't been taken into consideration. It's just that it hasn't been at the forefront of actually recreating a real experience. It's more an enhanced, immersive sort of engaging experience. So it's a very, very good point. Entirely valid route of further research to go out and measure real things and then try and recreate them in a different environment for the purpose of increasing fidelity. I'll take that.
Okay. Penultimate question from Ben Alden. Have you dealt with phase issues with multiple transducers attached to the same physical system?
Yeah, okay, things can get quite interesting when you have that. Haven't specifically ran into any huge issues with phase as yet. If everything's working in unison on a surface, as long as that surface isn't totally floppy, mostly it works out. You can do interesting things by manipulating the phase, however. If you invert the phase of one, you can imagine a tactile dipole, that kind of thing. It can get you can get some interesting effects out of it. So issues wise, not really. Again, if the system has had some form of thought put into it and it's quite rigid and solid, not solid, but you know what I mean, substantial, then yeah, you're probably not going to find massive issues with phase interactions.
Okay, and tonight's final question comes from Giuseppe. What is your understanding of distortion for shakers? Is it subjectively perceivable in your opinion?
Subjectively, yeah. Well, it depends on the type of distortion. You can get these things rattling away. Harmonic distortion, maybe not so perceptible because it becomes less of an issue as you go further down in frequency. The transducers are not capable of producing the upper harmonics as effectively as they are the ones down the bottom. So can I just have the question once more?
Distortion in transducers.
Distortion in transducer, is it perceptible? In my experience, no. The type of distortion that is perceptible is actually the sonic stuff. So in that respect, it becomes important. If you can hear it over what you're meant to be hearing, that's problematic. But usually you find that's more rattly buzz, that kind of stuff, like mechanical issues rather than harmonic distortion. Yeah.
Right. Okay, well that wraps up the questions for this evening's talk. It just remains for me to say to pass on all the thank yous from our attendees coming through the chat. Lots of thanks to you, Steve. And it just remains for me to say thank you to Steve himself for this fascinating talk. Thank you to everyone who attended, both your attendance and also the great questions that we put to Steve. Let's see if he knows his stuff, and turns out he does. So wearing his boffin hat on, just like to say thank you very much. As Steve said, keep an eye on the newsletter for future. Yeah, boom, boom, shake the room. Thank you, Jamie. Keep an eye on the newsletter for future AES UK events. And just remains for me to say good evening to everyone.
Thank you all very much. Really appreciate it. All right, until next time.
All the best.
Cheers.
Bye-bye.